we are discussing instruction set level architecture with the help of a very simple instruction set for MIPS processor. We have seen that this architecture has 32 registers, each of 32 bits, and there are very simple instructions with which we can perform arithmetic, add, subtract and other logical operations, and we have also looked at some branch instructions. We will continue further in that direction. Here is a summary of instructions we have discussed so far: add, subtract, add immediate and subtract immediate. The latter two are for operands which are constants. Similarly, we have and OR and their immediate version, and immediate and OR immediate. For comparison of less than or greater than type, we have SLT instruction, which also has an immediate version. So, in all immediate instructions, one operand is still a register and second operand becomes a constant. Then for equality and inequality comparison, there are BEQ and BNE instructions. For an unconditional jump, there is a J instruction or jump instruction. For moving data between memory and registers, there are load and store instructions. In particular, we have seen load word and store word, these two instructions. When you have to load a constant, which is a large 32 bit constant, we need to do it in two parts, and first we have to worry about load upper immediate, which loads the upper half, and then you can put back the remaining half or the right half. So, it is important to know what is the format of these instructions. Format is the way in which instruction is divided into fields. There are instructions which are of R format or register format, where apart from opcode you specify up to 3 registers. I format is required wherever there is a constant, either for performing an operation or for specifying an address. So, these are I format, where there is a field of 16 bits, so that a 16 bit constant can be provided. Yet another format was J format, which is for jump instruction, where 26 bits which are left after having a 6 bit opcode are used for specifying address. Okay, now, today we will continue further from this point and talk of how we can have further control constructs. We have seen a case of a simple if then or if then else type of structures, where a simple check using typically a BEQ BNE instruction, possibly in conjunction with SLT, could be used. Same instructions can be used for executing loops. We do not need to introduce new instructions, and we will see that. We will see that typically in a loop you access an array, and that can be accessed with index or a pointer. We will see what is the difference between these. We often need switch type of statements, where you need to take a decision which has multiple outcomes. So, we will see that, and finally, we will go into little more depth of how addresses are actually given in various MIPS instructions. There is a variation from instruction to instruction, and we would like to understand some of those subtle differences. So, let us start with a very simple example. Typically, probably the first thing you learn in your programming is summing elements of an array. Okay, so, it is a straightforward thing, although I have written in somewhat unusual form, where instead of using a for structure, I have put in terms of conditions and go to, so that I can easily correlate with what we are going to write in assembly language. So, A is the array and n is the size of the array. There are n elements. We begin by initializing a variable which is going to hold the sum. Then there is an index, and this is the main body of the loop, where you take element of array and sum it, update the index and perform loop termination check and go back. So, L is the beginning of the loop and this is the body of the loop. So, this is a header or prefix of the loop. Now, how we do this in assembly is what is of interest today. These instructions, these steps are implemented by very straightforward move instructions, where you move 0 value into some register. So, now remember the correlation between the variables and the register we are using. We are using S0 register for holding the value of sum. We are going to use T0 register to hold the value of the index. Okay. Now, here we have written a single statement S equal to S plus A I, but this needs to be broken down into a number of steps. First of all, we need to prepare the address to make an access to the array. So, as you know that each element, if you are talking of integers, is going to occupy 4 bytes. So, from the starting point of the array, the offset of A I would be 4 times I. So, we actually multiply T 0 with 4 and T 1 now contains 4 times I. This is added to the starting address of A. Okay. So, here I have just put a comment that S 1 contains address of A 0, the first element. So, these two when added together give you the address of A I, and once we have that, we can use load word instruction, and the offset here is 0. The word loaded comes to T 2. Okay. So, T 2 is a register which is temporarily used, and finally, this gets added to the running sum, which is in S 0, as you notice in the beginning. These two are added, the result is in S 0. So, it is 1, 2, 3, 4. These 4 instructions are actually doing the job of this statement, and then simply update the index, compare with S 2. I am assuming that S 2 contains n, the size of the array. Okay. So, T 0 which contains I is compared with S 2, and if T 0 is less than S 2, we branch off to L, that means start the loop again. Okay. Now, I have not talked of BLT instruction. BLT is a pseudo instruction. Okay, it is not a real instruction. In some tutorials I have mentioned that there are pseudo instructions which may correspond to one or more real instructions. So, what exactly is this particular one? BLT compares 2 registers, and if first one is less than second one, goes to label specified here. Okay, this is equivalent to actually 2 real instructions. One is SLT. SLT compares these two, but the result as a 0 1 value is stored in AT. Then you can compare AT with 0 and then make a branch. All right. So, what will happen is if R 1 is less than R 2, register AT will be set to 1 and it will not be equal to 0, and therefore, branch will occur. So, in tutorial we are going to see many more instructions like this and see how they can be implemented using SLT and BEQ or SLT and BNE. Okay. So, various kinds of comparison can be done, and once we understand that, we can simply use BLT as long as we have assembler which expands it for us, or we can expand it ourselves. This works fine. Now, here where is the cursor? Yeah, I have introduced another register AT. AT stands for assembler temporary. So, typically I am expecting that BLT will be expanded by the assembler, and as you know, there is a need for a register to hold some temporary value, some intermediate value, and by convention one of the registers is actually dedicated for this, and in terms of number, this is register number 1. We have already seen that register number 0 has a special role. Okay. So, which is by hardware, you cannot modify the contents of register 0, it always remains 0. AT or register number 1 is used by assembler, it is more by convention. There is nothing which hardware does in this case. If you want to use AT for some other purpose, you can do so, hardware will not restrain you, but then you can get mixed up with assembler's usage of it and your own usage of it. So, the convention is good to be followed. So, you would typically not use this directly and leave it for assembler to use. Okay, now, that was the core of the program which I talked of. How does the overall program look like? We have some assembler directives which define the data area and the code area. So, dot data is to be used when you want to define some data area. So, we are saying that A is a label here, there is another assembler directive dot space and there is a space which you are trying to leave of 400 bytes. What we are saying is that in the data area leave space for 400 bytes. I am assuming here that n equal to 100, we have array of size 100. Then there is dot text which indicates beginning of the code or the program. So, you will initialize these two registers which we assumed that S1 contains the starting address of the array. So, here we are using instruction LA which is load address into this register and A is the address we are loading. So, as a symbolic language programmer or assembly language programmer, you need not worry about what address actually A is, okay, you are leaving it for the assembler to figure out. If you do want to bother with the data directive, you can also specify an address here, okay, but here we have chosen not to, and assembler will assign some address in some default data area. So, A for us is a label, but internally A is an address and that address is getting loaded into S1. Assuming that A is an address which could be of arbitrary size 32 bits at most, this instruction is actually a pseudo instruction which will get split into these two real instructions. Okay. And this is what we had learnt in the last lecture, that loading a large constant into a register requires two steps. First step loads the upper half, next step loads the lower half. So, the two halves of the address I am denoting by A upper and A lower, right. A upper is loaded by LUI instruction into upper half of S1, and then this OR instruction simply superposes the lower half into the right portion of the register. Second initialization I wanted was that register S2 contains n. Okay. So, I am saying load immediate S2 100, 100 is a small constant. So, a single instruction can load it. Okay. You OR 0 and 100 and put in S2. So, with this preparation I am ready to go. You need some code to input the data, fill up the array for which you are going to perform the sum. Then there is code for computation, this is what we have seen already, and there will be some code for the output. Okay. Once you have done the summation, you have to output the result. So, I am skipping the details of input and output code, we are discussing that in tutorials. Right. Now, we have written some code which works, but can we improve it? So, here we would notice that using pointers or addresses directly rather than index, we can have faster code or improved code. So, on the left side here you see the same code which we have, and there is some modification made here. I am introducing a pointer p. So, this is still in high level language. I will show you how we do that in assembly language. So, p is a pointer which to begin with is pointing to starting address of the array. Okay. And when you are performing sum, instead of indexing the array A, we are dereferencing the pointer. Okay. So, instead of saying s gets s plus a I, you have s gets s plus star p. Then in addition to incrementing the index, we are incrementing the pointer and rest is same. So, these are the two extra statements we have introduced. One is initialization of pointer, updation of pointer. The summation gets replaced by this. So, although it may appear that I am introducing more statements, but when you translate this summation into assembly, you will find that you can do with lesser number of instructions. Okay. That is where the gain is occurring. And initially there is one extra statement, but in general we are more worried about making the loop efficient, because that is the one which is done several times. In this case it is just 100 times, but it could be 1000, it could be million. Okay. So, here is what we have indicated, and these are the instructions. Okay. Let me see how to. So, here is main body of the loop, where you would see that the number of instruction has reduced. Okay. This is the initialization of the pointer which I have introduced. I am sorry, this is okay. I think it says jump 2 steps further. Let me go to. Okay, I wanted to look at this first. Yeah. So, this is the initialization of the pointer. I am saying load address $T1 A, okay, and we have seen how such a statement gets expressed in terms of real instructions, and the loop has become simpler. This is simply loading the word and performing the addition, because address is already ready. In the previous case, we had to multiply the index by 4, add it to the starting address of the array, and then get the data from the memory. So, those two initial address preparation steps have been skipped here. You can straight away load the data from the memory and from the addition, and that is where the improvement is. This is an extra statement which has come. All right. So, although we have cut down something, we have added, but what we have cut down is much more, and what we have added is not all that much. The remaining part is same. Okay. Is there any question about this? Okay. So, having done that, we find that there is more opportunity for improving the code. You would notice what is happening here is that we are working with a pointer and an index, both are there, right. We are using index simply to control the termination of the loop. Question is, can we use the pointer itself to do that, instead of maintaining an index which we are not using to access the array. We have the pointer, and at the end of the loop we can check pointer if it has reached the final value. So, if we do that, then I can be eliminated altogether. Okay, how do we go? Okay, so here is an attempt to improve the code further. You have I equal to 0 initialization and I plus plus and this comparison, these all change. Okay. First of all, we have removed I equal to 0. We have added a statement which computes the final value of the pointer. Okay. We say that q is p plus 100, okay. And instead of comparing I with n, we can compare p with q. So, I plus plus is also removed and this comparison changes. Once again we have introduced a statement here, but we have removed there. So, there is not much of a difference and the loop is even shorter. So, we go back to assembly and see how this is done. This is the statement, this is the instruction which is preparing the final address, okay, the final value of the pointer, and we are keeping that in S2. So, S2 is equivalent to our q now. Although in high level language I said p plus 100, but I must be careful to add 400 here. Okay. It is 400 which is added here in place of 100, and S2 now contains the starting address of A plus 400, which is now the final address. So, rest is same and the comparison here is between P and Q, right. So, this is our final code after having all these improvements done. Okay. Now, having understood how a loop is programmed, let us take up something a little more complicated. What if there are two nested loops and you typically require that in sorting. Okay. So, here is a simple sorting algorithm. Okay. This is not definitely a efficient one. What it does is simply iterates over the array, okay, finds out the smallest one, places it at the first position, then looks at the remaining, goes over those, finds the next lowest and so on. So, there are two loops here. Once again I have not put for structures, I have used comparison and jumps. So, you would notice that there is one loop here, okay, which is beginning at y, and this is contained in another loop which is beginning at x. So, that is the outer loop. Inner loop makes a pass over the array. The main step, which I have not detailed here, I will look at it separately. Main step basically looks at one element of the array which you are currently scanning, and compares it with the element placed in the key position where you are trying to bring it. It compares, and if necessary interchange is done. So, this key position in the first outer loop, first iteration of the outer loop is the first position, then it becomes the second position and so on. So, what I am doing here is with the first with anchored at the first position, you scan rest of the array, then anchor with the second position, scan the whole array and so on. So, this is a comparison and interchange step. All right. What you need to focus here, what you need to worry about here is how these indices are changing, or in this case basically I am working with pointers. So, P is one pointer to begin with, it is pointing to initial position of the array. Q is again pointing to the end value. Okay. So, I am doing P plus 99. So, it is not pointing to the final value at which you will terminate, it is pointing to the last element. Okay. So, R would be second pointer, Q will not change in the process, it is P and R which will change. R will change in the inner loop and P will change in the outer loop. So, R gets initialized to p plus, I think this should have been p plus 1. Okay. In assembly I will say p plus 4, this please correct it to p plus 1. So, now R is initialized to this, and in the inner loop it is updated. So, we are basically comparing elements pointed by p and r, and if necessary interchanging, and this inner loop simply does that. P is not changed, R is updated, comparison is done, and you go through this. Once you come out of this, then you update p, okay, and repeat this process. Okay. R starts with a position which is next to that. So, once again it will translate very simply. The pointer initialization is load address. So, T 1 is carrying our p value. It prepares, next statement prepares q for comparison purpose. S 2 contains T 1 plus 396, right. T 2 is initialized to T 1 plus 4. So, T 2 is R. Main step again I will elaborate later. Then update R, okay. Do a less than equal to comparison here between R, T 2 is R, S 2 is Q. Update P which is in T 1, do a less comparison T 1 and S 2 which is P and Q. Okay. So, this is how the overall flow of control is, and now what remains is to elaborate on the main step. So, basically we are comparing elements pointed by p and r. If p element or element pointed by p is less than element pointed by r, we skip this interchange step. Okay. This interchange I am just showing it in abstract sense that p and star r are interchanged. Okay. This would require 3 assignments going through temporary and so on. I am not going into those details, but how we do interchange in assembly, that we had seen in the earlier lecture. So, all you need to do is load the values pointed by p and r into T 3 and T 4. Okay. Do this comparison, less than comparison. I am once again using BLT statement, which is a pseudo instruction. If I need to interchange, all I need to do is simply store the values in a cross fashion. So, T 3 and T 4, the order was T 1 and T 2, here it becomes T 2 and T 1. So, just store them in interchange manner, and here I am simply Z is a label which I am putting to the statement which was following it. So, if you go back after the main step, this was R plus plus statement or add immediate T 2 T 2 4. So, basically that statement, it is not that you are putting once more, I am just indicating that Z is a label which is there just to make sure that you come out of this part. All right. So, once you understand how comparison is done and how branch and jump instructions are used, the loops can be implemented in a very straightforward manner. Another control structure which you often encounter is that you have some value which could lie in certain range, and for different values you need to do different actions. So, unlike a Boolean comparison where you have true and false outcome, here you have some expression which you evaluate and the result falls in certain range. So, as an example, suppose you have a value k, okay, which can be either 0, 1, 2 or 3, and small pieces of code you have for each case, you will capture it by a switch statement. Okay. And with after each you want to break, that means after performing f equal to I plus j, you do not want to go through all of them, you want to skip and come to the end, you put a break statement. Of course, the last one is not necessary, but just to make it look uniform I have put it there. So, how do we do that? One option of course is that you can make repeated comparisons. right. You compare k with 0, check if it is equal to 0 or not, do this action, then compare with 1, compare with 2, compare with 3. With the range just being 4, it is not all that difficult, but if the switch statement had lots of cases, then this will become very tedious and messy. So, there is a more elegant way of doing it by doing a multi-way branch by a single instruction. So, a new instruction which is JR, jump on register content, which will be used here. So, we will do this with the help of a table. Okay. What we have is that in a table we have all the starting addresses of different cases, okay. And then we simply look at the value of k, use it to pick up the right address from the table and jump to that. So, let us see how it is done. Initially I am making sure that the value k falls within the range 0 to 3. If it is outside, then I want to skip, right, because my table will not have entries corresponding to it. So, yeah. Assuming that S 5 contains k, first it is compared with 0. If S 5 is, if k is less than 0, then I skip. Second comparison is made against 4. Okay. So, if this is greater than or equal to 4, again I exit. Okay. So, label exit would be somewhere at the end here, I have not shown it. Once that is done, then I need to prepare an index for the table from where I am going to pick up the destination address. So, basically I need to obtain 4 times k. Okay, each address in the table is going to occupy 4 bytes of one word. So, here you will see that there is a different way of performing a multiplication by 4. I am simply doubling the number twice, and that gives you 4 times its value. So, add T 1 to itself, the result goes to T 1. I think I should have there should be one more add statement like this. I am sorry, there is you do it twice. This is doubling T 1. No, I am sorry. Oh, okay. Yeah, we are starting with S 5. First we have doubled S 5, got into T 1, then double it further, got into T 1 again. So, we have 4 k. Then T 4 is assumed to have address of the jump table, starting address. The way we prepared the index for, the way we prepare address for the array, same thing is done. So, starting address is added, and now final address is in T 1. So, this contents of memory location addressed by this are loaded into T 0, and then I say JR T 0. Okay. So, this is this exercise is to jump to an address which is contained in a table, and which address from the table we pick up is determined by k. Okay. So, the 4 cases we had are now listed here. They are at labels L 0, L 1, L 2, L 3, and the table is shown here L 0, L 1, L 2, L 3. These are the 4 addresses kept in this table, and register T 1 finally is made to point to the appropriate address in the table, and we are jumping to that. So, the statement we had in the first case, now recall this, we have I plus j in first case, g plus. So, there is an addition here, another addition there, and then 2 subtractions. So, you will find straightforward code doing that. S 3 and S 4 are added, put in S 0. This is the other addition, subtraction, another subtraction. So, whatever the code is, whatever is the body of the case can be put here. It could be one statement, it could be more statements, and finally, you have jump to exit, which is corresponding to the break we had. Okay. Now, this looks nice for a simple case, but problems could often be more complicated. If you are talking of values which are not contiguous, here we had 0, 1, 2, 3, all 4 values were relevant, but if you have non-contiguous values, then the table could be sparse, you would waste the space, and if it is too sparse, it may still be better to do repeated comparisons. But if the range is compact, that means you are interested in almost all the values of the range, then the table approach may be fine. In very specific cases, when these 4 labels are let us say equally spaced, okay, if they are uniformly spaced, or they can be or these bodies of the cases can be padded up with blanks to make them uniformly spaced, then you do not really need the table. Okay. So, suppose suppose these addresses are 1000, let us say 1020, 1040 and 1060. So, they are uniformly spaced, all right. Then instead of table, what I need to do is I take the starting address 1000 plus 20 times k. So, I need to simply compute this and then do JR with that, right. Instead of looking up these 4 addresses in the table, this is fine, this is a general approach. If the addresses are arbitrary, but if they are uniformly spaced like this, then I can simply compute the address by taking a base address plus some constant times k. So, that sometimes that is much more efficient. Okay. Now, let us get back to this range of instructions we have talked of and see how address is being actually specified in these. So, we have so far seen branch instructions, EQ, NE comparison. I will not look at BLT, BG and so on, because they are ultimately built using BEQ and BNE. Then we have load store instruction, which all these used I format, where a 16-bit number was specified and that was used in computing the address. J instruction had a different format, J format, where there is a 26-bit number specifying the address, and we have now today seen a new instruction JR, which is actually in R format. So, although R format provides fields for 3 registers, we require only 1 here, others are left unused, okay, but the format is R, and the remaining these 3 fields are unused. So, now in these 3 cases, how do we specify, how do we really get the address given an instruction, and we will even look at these 2 and LWSW separately. So, first let us begin with load and store. So, imagine instruction of this type, load word R1 C R2, where C is the constant part and R2 is the register. This is also called index register or base register. So, the exact effect of this is that the memory location which is being addressed is obtained by C plus R2, these 2 are added, and the thing to be noted here is that C is an offset which could be positive or negative, right, and as a 16-bit number, the value of this offset lies in this range 2 minus 15 to 215 minus 1. Okay. This is in 2's complement form. If you are familiar with 2's complement notation, you will immediately recognize this. but if you are not we are going to talk of this representation in detail later on. So, at the moment you can just notice that the offset could be positive or negative in certain range, right. And the address which is being specified here is a byte address. In BEQ BNE we will actually have, we are worried about word address. So, whereas data could be in terms of bytes or words or double words and or half words, all those varieties may exist. Instructions in this architecture are all one word instruction. Later on we are going to see processors where instructions could also be of varying size, but here we have simplicity that all instructions are 4 bytes or 1 word. Therefore, the instructions are always located at aligned boundaries. The instruction addresses are always multiples of 4, and that fact is made use of. So, the offset, the address which is being provided here is actually an offset, again positive or negative, with respect to the current position in the program. So, in a program if you are jumping 4 instructions ahead, then you will give a positive offset corresponding to that. If you are jumping back like in a loop we had, you will have a negative offset. So, when you are using assembly language, you simply write a label, and the label of destination could be after the current instruction, it could be before the current instruction. Assembler will automatically generate a corresponding offset, either a positive or negative. The offset here is in terms of word, okay. It is not a byte offset, it is a word offset, because we know that addresses for instructions are always multiples of 4. So, the meaning of this instruction exactly is shown here. BEQ R1 R2 C compares R1 R2, and PC, which is the program counter, that is the register specifying address of the current instruction, it becomes PC plus C, but strictly speaking notice that there is a plus 4 also. So, the offset is not with respect to current instruction, it is with respect to the following instruction. Okay. There is a subtle reason which is related to the hardware implementation of this, that why we are keeping PC plus C plus 4 and why not simply PC plus C. Okay. So, it is for some hardware convenience which we will see later. So, for the moment you can just notice that depending upon the outcome of comparison, the next value is either PC plus 4 or PC plus C plus 4. It should actually be PC plus 4 C plus 4, because C is a word offset. The next instruction follows similarly. Okay. What happens in a jump instruction? In jump instruction, we are specifying a 26 bit number as the destination address, but we need a full fledged 32 bit address finally before we can proceed further. So, the effect of this instruction is as follows, that once again first PC is incremented to PC plus 4, okay. Although we are not going to the next instruction, but this happens automatically. This happens sort of without in terms of hardware, PC gets PC plus 4 happens without even bothering whether it is a jump instruction or a branch instruction or something else, and after that we see how rest of the address is computed. So, these 26 bits of the instruction, which I am saying instruction 0 dot dot 25. So, these are the LSB 26 LSBs of the instruction corresponding to this field. They are placed in position 2 to 27 of the instruction of the PC. Okay. Bits 28 to 31 of PC are unchanged, and bits 0 to 1 are 0 and they remain 0. Okay. So, now what it means is that using J instruction you cannot jump anywhere in the memory space. You can specify a range which is defined by 26 bits. Okay. and this 26 bit number is taken as a word address. So, effectively in terms of bytes it is effectively 28 bits. So, your range of jump is within the current segment of size given by 2 raised to power 28 or 256 MB. So, if you imagine that the memory is divided into segments, okay, with 32 bits you can get 4 GB of memory, 2 raised to power 32 is 4 GB. Imagine that 4 GB space is divided into segments of size 256 MB. So, your jump is occurring within the current segment. So, let me illustrate that. So, suppose this is 4 GB, and each of the segments is 256 MB. So, if your current instruction is here, you can jump anywhere in this region. Of course, there will be an exception case if the jump statement was the last statement of a segment, then jump will occur in the next segment because of this initial value of PC. PC is initially incremented by 4 and then you are figuring out where to jump. So, typically you will be somewhere within the segment and jump will occur within the segment. If you are at the last point, at the last word of the segment, then the jump will occur in the next segment. Okay. Lastly, we look at JR, which is very simple. You are specifying a register which is a 32 bit register. All that you are doing is transferring the contents of that register into PC. So, here you are specifying a full fledged 32 bit address and this can be used to jump anywhere. So, most of the time J instruction would suffice when you are simply jumping to a constant address, but if you want to jump to a far off segment for some reason, you will have to use JR again. We have seen JR used for a different purpose. We have seen how JR is used for a switch statement, but JR can also be used for carrying out a jump when the destination is far off. Okay. Finally, let me summarize about what we have learned today. I began with examples of some loops, how we can use simple compare and branch statements to carry out simple loops, nested loops. We have seen that when arrays are being accessed sequentially in a loop, there are opportunities for improving the code. You can do more computation before the loop begins, so that the loop is a tight loop, it is efficient loop, the body is more compact. And now, what is the importance of these improvement? As I mentioned earlier, you are likely not to program in assembly language in practice. So, what is the point in bothering about these small nitty-gritty improvements? These are important from the compiler point of view. So, the way we try to improve the code, that understanding is required for compiler writers, because they have to generate code which is efficient, and these transformations, these improvements should be kept in mind by a code generator of the compiler, so that efficient code is generated. So, given the kind of example we took in the beginning, actually compiler can automatically generate the final improved code from the inefficient program we wrote initially. So, that means you might write using index, but compiler can always convert it to the final form. So, these are very systematic transformations which can be used to do that. We also saw how we can implement a switch statement using a table and JR instruction. And finally, we have seen in a very subtle manner how various instructions address the memory. Okay, there are different ways in which address is computed in different instructions, and we have gone through those details. So, I will stop at this point.